we've already looked at one way to determine empirical and molecular formulas using experimental data. In that way, we were simply told either the grams of each element that were determined or the percentage of each element that was determined. And we followed a basic three-step process where one, we converted things into moles. So if we had grams, we turned those into moles. Two, we wrote a pseudo formula. So that was something like CXHY or something like that, or however many moles we got, we put in to those subscripts. And three, we would divide the subscripts by the smallest number possible. And that should have given us whole numbers. So you convert to moles, write a pseudo formula, divide by the smallest subscript. Now we want to do a very similar process, but using a technique called combustion analysis. Combustion is exactly what it sounds like. You burn something. So in combustion analysis, you take your unknown substance and put it in a furnace. You fill the furnace with oxygen and you burn it. And then, depending on how exactly you decide to perform this, there are ways to isolate all of the products that you produce. Typically, any carbon that you had in your original sample is going to combine with that oxygen to form CO2, and any hydrogen you had in that particular sample is going to combine with oxygen to form H2O. If you have other elements, they'll also combine with oxygen, but we're really just going to focus on these two. So we're going to focus on hydrocarbon compounds, so those that contain carbon and hydrogen, and how they combine with oxygen. So in a combustion analysis problem, instead of being told how much carbon and hydrogen you end up with, you end up being told you end up with this much carbon dioxide and this much water. And we have to use those products to figure out what we started with. So it's similar, but it has this extra step in the beginning. So in a combustion analysis problem, you weigh your products, which are typically, again, CO2 and H2O, and we need to extract just how many moles of carbon and hydrogen were in that, because we added the oxygen. That wasn't part of our original sample. So we're going to weigh our products and then do a simple two-step process to turn our grams of either CO2 or H2O into moles of each compound. And then we can look at the element to compound ratio and figure out how many moles of carbon or how many moles of hydrogen. So we did this in our composition of compounds section where we learned to relate a particular element to a particular compound, and we're just going to do that again here. So good news is for combustion analysis, these steps are always exactly the same. The only thing that's different is exactly how many grams you start with. After you end up with your moles, you follow the same steps as before. We write a pseudo formula, we divide our subscripts by the smallest number. So let's look at an example. Upon combustion, a sample of an unknown hydrocarbon, so it only contained hydrogen and carbon, produced 1.60 grams CO2 and 0.819 grams water. Determine the empirical formula. So we're in combustion. So we have a combustion analysis problem, and it's starting me off with 1.60 grams of CO2 and 0.819 grams H2O. So I need to recognize that this is a combustion analysis problem. It eventually wants an empirical formula, and I need to recall that if I only have a hydrocarbon, I just want to figure out how much carbon and hydrogen. I don't care about the amount of oxygen here. So I need to turn these grams of CO2 and grams of H2O into moles of carbon and hydrogen. Fortunately, we know how to do that. So we're going to get rid of our grams of CO2, and the only thing we can relate that to right away is our moles of CO2. So we use the molar mass, 1 mole of CO2. If we add up those elements, carbon and 2 oxygens, it's equal to 44.01 grams. And then we want to get rid of moles of CO2 and turn that into moles of carbon. There's a C in front of that. So now we just look, CO2, for every 1 CO2, there is 1 carbon. So we get rid of our grams of CO2, our moles of CO2, and end up with moles of carbon. And if we do the math, we get a pretty small number, 0.03636 moles of carbon. Now we'll do the same thing for the water. First, we want to get rid of those grams. You have to turn it into moles of water. So every 1 mole is equal to 18.016 grams. So that's just adding up 2 hydrogens and an oxygen. So I'll get rid of the grams. But we don't want to stop there. We want moles of hydrogen. We want to get rid of the moles of H2O. So for every one molecule, there are 2 hydrogens. So it's really important we get that correct mole-to-mole ratio. So now my moles of water cancel, and I get moles of hydrogen. So again, do the math on this, and I get 0.09092. All right, now that I have moles of the element, now it's just business as usual. I'm going to write my pseudo formula. So I'm going to have carbon, give him his moles, 0.03636. I'm going to have my hydrogen, 0.09092. So I'm going to write my pseudo formula, divide both of these by the smaller number, which is the 0.3636. So of course those cancel and just give me 1. And when I do that, I get 2.5. So here's one of those instances where I recognize, all right, I can't just stop here. I have a 1 and a 2.5. I can't have a decimal. So I need to turn these into a whole number. So I'm going to multiply both of these by 2, because 2.5 times 2, that'll give me a whole number. So I'll end up with C2H5. 2.5 times 2 gives me 5. So that's my final answer for my empirical formula. So everything starting from here was exactly as we've learned before. We wrote a pseudo formula divided by the smallest number. We did have a decimal in this case, so we got rid of it by multiplying by a small whole number to get our final answer. The only thing that's different is that instead of starting with grams of carbon or grams of hydrogen, we started with grams of a compound, and we had to use our knowledge of those gram-mole-mole conversions to turn it into moles of the individual element. But that's how all of my combustion problems are going to look, and we're only going to worry about them with hydrocarbons, so we're only really going to worry about these 2 steps.